Welcome. Have you ever wondered how Google knows the next word you're about to type? Or how economists predict market trends? Well, the secret often lies in a surprisingly powerful mathematical tool called a Markov chain. Today, we're going to pull back the curtain and see exactly how this tool lets us predict the very next step in almost any complex process.
So, let's start with a little riddle. What could biology, business, and physics possibly have in common? I mean, tracking a disease, analyzing customer behavior, and understanding particle physics seem like they're worlds apart, right? But it turns out they all share one powerful fundamental analytical tool. And here's the answer, the secret sauce. All of these fields use mathematical models that predict the future based only on the present state. Just think about that for a second. The past, everything that came before, it just doesn't matter. This simple but really powerful idea is the absolute core of the Markov chains we're going to explore today.
So, here's our game plan. We'll start with an introduction, then get into the basic building blocks. After that, we'll walk through a hands-on example, see how to actually calculate predictions, and finally, wrap it all up. Let's get started.
All right, let's dive right into part one. What exactly are Markov chains? We're going to lay the foundation for everything else we'll build on.
In simple terms, a Markov chain is just a series of events. But the magic is in something called the Markov property. The probability of the next event happening depends only on the current state. Everything that happened in the past, a second ago, a year ago, is completely irrelevant. You could say it has a really short memory.
Okay, so to really get how these chains work, we need to break them down into their core components. There are basically three key pieces that work together to make the whole thing tick.
First up, we have the probability vector. Think of this as a snapshot of the system at a specific moment in time. It's got two simple rules. All its values have to be non-negative, and, most importantly, they all have to add up to exactly 1, representing 100% of all possibilities.
And here's a perfect example. If 60% of a population lives in the city and 40% lives in the suburbs, the state vector that represents the snapshot is simply 0.6, 0.4. And as you can see, 0.6 plus 0.4 equals 1, accounting for 100% of the population.
The second component is the stochastic matrix. Now this is the rulebook. It's the engine that dictates how the system changes over time. It's a square matrix where every single column is itself a probability vector, describing the odds of moving from one state to another.
And now we tie it all together. The Markov chain itself is simply the sequence you get when you take your current state vector, xk, and multiply it by your rulebook, the matrix P, to get the next state, xk plus 1. This simple equation, xk plus 1 equals P times xk, is the engine that drives the entire chain forward step by step.
Okay, enough with the theory, right? Let's see how all these concepts actually work together with a concrete real-world example: population movement between a city and its suburbs.
So, let's go back to our population example. In the year 2014, we had 60% of people in the city and 40% in the suburbs. This gives us our initial state vector, our x0. This is our starting point.
And here comes our rulebook, the migration matrix M. This tells us exactly how people move each year. Let's read it together. The first column represents people starting from the city. We see 95% of them stay in the city, while 5% move out to the suburbs. The second column is for people starting from the suburbs. Of them, 3% move into the city, while the other 97% stay put.
All right, now for the exciting part. We're going to use these components to actually predict the future. We'll do the math together, step by step, to see what the population distribution will look like next year.
So our goal is to find x1, the population distribution for 2015. And to do that, we just apply the formula we learned. We multiply our rulebook matrix M by our initial state vector x0.
Let's break this multiplication down into two simple steps. First, we'll calculate the new percentage of people in the city, and then we'll do the same for the suburbs.
For the city, we figure out who's staying, that's 95% of the original 60%, and we add the people who are moving in from the suburbs, which is 3% of the original 40%. When you add those up, you get 0.582. This means we predict that 58.2% of the population will be living in the city in 2015. And we do the same thing for the suburbs. We take the people who moved out of the city, 5% of the 60%, and add them to the people who stayed in the suburbs, 97% of the 40%. And that result is 0.418, or 41.8%. And notice, if you add our two results together, 58.2% and 41.8%, you get 100%. So our math checks out perfectly.
And this is the beauty of the chain. We started in 2014 and predicted 2015. Now we can just take our 2015 result as our new current state, multiply it by the same matrix, M again, and predict 2016, and so on, as far into the future as we want.
So after all that, what's the big idea we should take away from this? Let's quickly recap the main points.
So what's the bottom line? Remember, Markov chains are a story unfolding one step at a time. Each step, a probability vector, is guided by a set of rules, the stochastic matrix. But the absolute most important takeaway is this. The next step depends only on where we are right now, not how we got here. This stunningly simple idea is what makes it such an incredibly powerful tool in everything from finance to genetics.
And now, I have a question for you. Where could you apply this idea in your own life or work? Think about weather patterns, customer behavior, maybe even your daily moods. Could any of those be modeled as a Markov chain? The real power is learning to see the world around you as a series of states and probabilities. Thanks so much for joining me.